This is Walter Leite, and in this presentation, I will provide an overview of propensity score estimation. So, to estimate propensity scores, which you can then use for matching or weighting to reduce selection bias in quasi-experimental studies, you need to go through a series of steps that include preparing the data set, estimating propensity scores, and evaluating whether you were successful. So the formal steps start with selection of covariates, where you identify true confounders and predictors of the outcome that you would like to include in the propensity score estimation. Now, these covariates will frequently have missing data, which brings us to the second step, handling missing data, and that can be quite complex and goes into, there are many methods available, such as multiple imputation. Now, once missing data is handled, we go to the propensity score estimation itself, where we can use parametric models such as logistic regression or non-parametric machine learning methods such as random forests. And then finally, once we have the propensity scores estimated for all individuals in the sample, we will look at common support, which is comparing the distribution of propensity scores across treatment and control groups. And I will go through these steps in more detail. Now, first, let's talk about an example to frame this discussion. The example comes from my book, Practical Propensity Score Methods Using R, and it is shown in chapters 1 and 2 of the book. So in this case, the question of interest is, does participating in a career academy in high school affect future income? The data source is a public data set available at the National Center for Educational Statistics website. It's the Educational Longitudinal Study, and it's a complex representative national study that used two-stage stratified sampling. And because of that, and also the fact that it oversampled some students, we will need to use sampling weights that come with the data set in order to do any type of statistical analysis, including the estimation of propensity scores. Now, the treatment measure here is the answer to a question: have you ever been in any of the following courses or programs in high school? And one of the options is career academy. So individuals that answer yes to that question are in our treatment group. Individuals that answer no are in the control group. In this particular data set, the proportion treated is 8.5%, which is very typical of quasi-experimental designs, where if you have a large national survey, the proportion treated tends to be substantially smaller than the proportion untreated. Now, going into selecting covariates to add in the propensity score model, we need to think about what type of covariates we want to include. Now, this is a very important step because propensity score methods only remove bias due to observed covariates. And if you have an unobserved confounder that's important, that will result in bias in your treatment effect estimate. So the important variables that you want to include are true confounders, which are defined as a variable that has direct effect on both the probability of treatment and the outcome. And so ignoring this variable provides a backdoor path for getting from the treatment to the outcome that is not the direct effect of the treatment. Therefore, it results in a bias estimate of the treatment effect. Now, it's impossible to know exactly what a true confounder is, but based on theory and reviewing previous papers about mechanisms related to treatment outcome, we identify from the variables available in the data set which was likely to be true confounders. Now, it's also important to include predictors of the outcome for a different reason. So predictors of the outcome, if you ignore them, it doesn't result in bias in treatment effect estimates. However, including predictors of the outcome in the propensity score model will increase efficiency, so it will reduce variance, giving us more power to detect the treatment effect. Typically, the most important predictor of the outcome is a pre-test measure of the outcome if available. In other words, either a measure of the outcome that was taken before treatment exposure or a proxy of the outcome that was measured before treatment exposure. That variable may be a true confounder too, but even if it's not, if it's just an outcome predictor, it's very important to include it because it will increase power. Now, treatment predictors are variables that are unrelated to the outcome and only related to the probability of treatment. Typically, we don't know exactly. It's hard to differentiate between a treatment predictor and a true confounder, including treatment predictors that are unrelated to the outcome will decrease efficiency and decrease power, but it's a trade-off. We typically include those, even though it's ideal not to, but sometimes it's better to err in the sense of caution, given that it's hard to differentiate between a treatment predictor and a true confounder. Now, what we don't want to include ever in the propensity score model is a mediator, right? Because a mediator is a consequence of the treatment, and including a mediator in the propensity score model will essentially be blocking that path from treatment to the outcome. So you're essentially removing part of the treatment. Now, in terms of true confounders, we want to include, as many as we can. Typically, a propensity score model has a very large number of covariates because of trying to make sure that the assumption that there are no omitted confounders is tenable. Typically, the mechanism to identify covariates is looking at literature, doing a theoretical analysis of the literature about antecedents of treatment. Also, pilot studies may help with the identification of the selection mechanism. Expert reviews may happen. Interviews with participants asking, like, why did they sign up for the treatment? That is a direct, way of trying to get data about the treatment selection mechanism. Okay. Now, for the specific career academy example that we're talking about, these are some variables that are available from the ELS study that could be good candidates for true confounders. Parents' highest level of education, home literacy resources, number of academic risk factors in 10th grade, and so on. Now you can see that the first 5 in this list are child or student level confounders, potential confounders, and the last 2 are school level potential confounders. So you have to think if your data is hierarchical, in other words, here the data is hierarchical because students are clustered within schools. There could be both individual level confounders and group level confounders. So once you identify a set of covariates, there will be missing data most likely, and you have to think about how to handle it. Listwise deletion is rarely viable because that consists of removing all observations with at least a BC value. And if you have a very large number of covariates, it may be that every observation has a BC value somewhere. So you may lose all your data. And also, least-wise deletion assumes that data is missing completely at random, which is a very strong assumption. So that should almost never be done unless you have a very small percentage of missing data in just a couple of covariates. Now, single imputation is a viable method, and I'll talk a little bit more later on when to use it. There are many ways of doing single imputation. You want to use a method that adds some randomness to the imputed value. In other words, you don't want imputed values that fall exactly on a regression line, because that artificially reduces variability in the data set. In multiple imputation, it's considered a best performing BC data method, and there are two major variations: joint modeling and multiple imputation, or multivariate imputation by chain equations, which is called MICE. Either one is viable here, but typically MICE is easier to implement because you only need to worry about distributions of covariates by themselves instead of thinking about the multivariate distribution of covariates. Though these days there are software that can do multiple types of covariates for joint modeling through mixtures. Okay, so reviewing this, listwise deletion, almost never viable. Single imputation with a method that adds some randomness to the data set. So, for example, you could do multivariate imputation by chain equation MICE, but only request one imputed data set, and use a predictive mean matching as that single univariate imputation method. And that works well with the propensity score. The proportion of missing data is not very large, I would say, less than 40%. In general, it's hard to provide a cutoff on how much, but large proportion of missing data, single imputation tends not to do well. Multiple imputation is our to-go method in general, and there are two ways to perform it specifically for propensity score analysis. One is the multiple imputation of covariates following by averaging the propensity scores, the estimated propensity scores across the imputed data sets and proceeding with the analysis with a single vector of propensity scores. So that is referred to as multiple imputation across. Now, the next method is obtain multiple imputed data sets and perform the entire propensity score analysis all the way to the estimation of treatment effects, separate for each imputed data set, and then combining the estimates of treatment effects. That is called multiple imputation within. Now, in general, multiple imputation within the second type has some theoretical advantages, but multiple imputation across works well. And I provide details in a simulation study evaluating the performance of the first approach, where you average multiple propensity scores to create a single propensity score vector. I showed that in this paper, imputation of missing covariate data prior to propensity score analysis, a tutorial and evaluation of the robustness of practical approaches. Okay, once you handle missing data, you can proceed to the actual estimation of propensity scores. There are two groups of strategies: statistical models that are parametric, logistic regression by far the most used one, and statistical learning algorithms, also known as data mining methods or machine learning algorithms. Now, the disadvantage of the statistical models is that you actually have to specify a model. You have to specify the functional form of the relationship between covariates and treatment assignment. So, for example, you can have a model, most commonly a model just with main effects of the covariates. You can add interactions between the covariates. And logistic regression is popular because even though there could be interactions, usually a logistic regression model with just main effects can perform well, and does in a lot of cases. Now, machine learning algorithms have the advantage of not requiring that a functional form of the relationship between covariates and treatment assignment be explicitly specified, and they can automatically detect interactions and quadratic cubic effects and so on. Now, in theory, they should perform better than parametric models because you don't have to specify the functional form. Now, in many cases, logistic regression works equally or better. So my advice is test at least two methods, one for each of these groups. Fit a logistic regression, and then use a machine learning method and compare the results with respect to common support and, most importantly, with respect to covariate balance. Now, because this is, we're trying to balance the sample, it's not, we are not doing statistical inference here. It's just try to balance the distribution of covariates. It doesn't really matter if you use 2 propensity score methods or 100 propensity score methods, because you are not inflating type 1 error by doing this, like you are not doing statistical inference. So you can try multiple methods and see which one gives you best covariate balance. So logistic regression, here is an example of a logistic regression model with just main effects of covariates x1 to xk. And the propensity score is the probability of treatment assignment. So, if you have the logit of the propensity score, you convert it back to a probability, as it's shown here, to be able to proceed. If you're doing matching, typically we just match directly on the logit of the propensity score. But if you were doing weighting, you need the propensity score itself, like the predicted probability. Now, for machine learning methods for propensity score estimation, a very popular class of methods are methods that make use of classification regression trees. So I will talk about classification regression trees here, but as you see, I don't recommend it as an actual method to estimate propensity scores, but I will recommend ensemble methods that use a collection of classification regression trees. Okay, so classification trees are for predicting a binary variable, and regression trees to predict a continuous variable. So if you were using these to estimate propensity scores, you would be using a classification tree, and the idea here is recursive partitioning. So you take each covariate and you split into 2 nodes that are more homogeneous with respect to receiving the treatment. Now, before deciding on which node to split, you would evaluate all nodes and select the split that minimizes impurity. So you want the largest gain impurity detection reduction. There are different measures of impurity. Now, as you do this recursively, variable by variable, you always try to select the variable that reduces impurity the most. But it's possible to, in multiple iterations, return to the same variable. So the variable, same variable can be split multiple times, which allows to capture complex relationships between that covariate and treatment assignment. And this is done recursively until stopping criteria. Okay, this is an example of classification tree to predict enrolling career academy. So you see the first split at the top was on the a race variable, and categories, which is a categorical variable. Categories 2, 4, 7 went to a node. Categories 1, 3, 5, 6 went to a different node. And then there was another split, and then that kept going until you end up with the terminal nodes here. Now, the reason we don't use classification trees directly to estimate propensity scores is that it has been shown that it doesn't work well with many covariates. That to overfeed the data, and covariates with many categories of continuous covariates tend to dominate. So there is pruning that can be done, but it still doesn't work well. What works well is ensemble methods, which are collections of trees, of classification regression trees, depending on the ensemble method. And so they run many trees and they combine them. So popular ensemble methods are Baggy, random forests, and generalized boosted modeling, GBM. So Baggy and random forests. So Baggy stands for bootstrapped aggregation. You run a large number of trees with bootstrapped samples and then take in with replacement and then combine the results. Random forest is a similar idea, using bootstrapped samples, but instead of using the same variables here for every tree, it takes a sample of variables. This is a nice improvement over Baggy, because since you're not using all the variables at each iteration, you prevent variables from dominating the results. So it explores better the space of solutions here. Now, so the steps is resample the data set, build a prediction model, or each resample data set either with all variables if it's Baggy, or a subset of variables if it's random forest, and then average the prediction. Generalized boosting models also use trees, but with a different idea. Here you're trying to minimize error, and in this case, because error is continuous, you're actually using regression trees. So it's an ensemble of regression trees instead of an ensemble of classification trees. So you typically for propensity score models, you try to improve prediction of the logit of treatment of assignment. So you start with baseline prediction, which is used the proportional treated to calculate the logit, and then using trees, regression trees, to minimize the within node sum of square residual. In this case, the treated value minus the propensity score. So with GBM, there is no stopping criteria. Now, a specific implementation was developed by McCaffrey, Ridgway, Morrell in papers in 2013, 2004, where they evaluate covariate balance you can choose a specific measure at each step and use that as a criterion to stop the GBM algorithm. So this is an implementation that is available in R in the Twang package that is specifically for propensity score estimation because it uses the goal of optimizing covariate balance as the stopping criteria for GBM. Now, it's important that if the convergence criteria, the stopping criteria, is met, if it's met close to the maximum number of iterations, it is important to run it with a larger number of iterations just to make sure that that was a local solution. So here, for example, you can see that the maximum number of iterations was 10,000. So the iterations is in the x-axis, and the covariate balance measure is in the y-axis. But you can see that the minimum in terms of balance measure was achieved around 1,000. Therefore, this is a comfortable solution here because we ran up to 10,000 and saw that solutions did not improve again. Now, if we had run it with just about 1,000 iterations or 2,000, we would want to run more because the graph would look different, showing that the minimum was pretty close to the maximum number of iterations. So once you finish estimating propensity scores with multiple methods, the quality of the propensity score is evaluated in two ways: through checking common support and to checking covariate balance. Now, I won't discuss covariate balance in this video because checking covariate balance first requires implementing the propensity score method of choice that can be matching, that can be weighting, or stratification, right? So it's beyond just estimating the propensity score. But what you can do at this stage is check for common support. This is a preliminary check because also different propensity score methods have different common support requirements. Like the common support requirement for matching is different than for weighting. And I will not discuss the difference here, but the preliminary check is to see if there is some areas of propensity score distribution where there are cases for both treatment and control. And this preliminary check is graphical. We look at visualizations, and it's just to detect the most outrageous problems with common support, which would lead you maybe to abandon propensity score analysis if common support is not adequate. Now, there is an assumption here that you should check too, the assumption of positivity, or also known as overlap, that there are no propensity scores that are 0 or 1, like the distribution of propensity scores is all greater than 0, less than 1. Now, so how do we check common support, like this preliminary visual check? Box and Whisker plots, density plots, histograms are common. We look at the minimums and maximums for treatment and control groups. Now, this is a preliminary check. Now, when you do matching, you have a better check later, is to check if there are unmatched units. If you are doing stratification, there is a check to see if there is any strata with 0 cases for a treatment or control group. Those are checks you do after you implement matching or stratification. The weighting doesn't have a specific check like matching stratification does, but you could look to see if there is extreme weights, which are maybe an indication of common support problems. So I'll just show you the visual check here. So, for example, for the Career Academy example, this is a box and Whiskers plot. You can see that there are some individuals in the control group that don't have any propensity scores in that same area of the distribution for the control group. It doesn't seem to be serious. Only 3 individuals here. So this preliminary check here seems okay. For random forest, probably seem a little bit worse. You can see like worse common support with random forests. Oh, by the way, this random forest was implemented with the party package. One thing about machine learning is that different software may give you different results. Now, this is implemented with GBM. Also seem a bit worse than logistic regression. As you can see here, there's a bit more of a separation. So from this preliminary plot, it seems like logistic regression did best in terms of common support. Now, if you had imputed data sets, let's say you had 5 imputed data sets from handling the missing data, you would check common support for each imputed data set, which is shown here through kernel density plots, which is another method. Okay, so if common support is just terrible, it may indicate that the treatment and control groups are too heterogeneous. Therefore, you may not succeed in implementing a propensity score method. You may want to look for something else. But the in many cases this works, and then you can proceed to actually implementing matching, weighting, or stratification. Okay. So to finalize, here are some packages that can be used in R to estimate propensity score. So logistic regression can be done with the GLM function that comes with the base package in R. However, if you have sampling weights, you don't want to use GLM for logistic regression. You want to use a package that properly uses sampling weights in the estimation of logistic regression. And a package that is very good at that is a survey package, and you would use a combination of this SVY design and SVY GLM to estimate propensity scores. For random forest, there is the party package, but there are others too. And again, the packages may provide different results. For GBM, the Twang package is excellent because it's one that was developed specifically to implement GBM for propensity score estimation. And then a front end to a lot of methods is the weighted package. I mean, even though it's designed to calculate weights, it estimates propensity scores first, right? So even if you are not doing propensity score weighting, if you're doing propensity score matching, you can still use a weighted package. And it's a front end for a very large number of machine learning methods. So it's a very helpful package. So that's options you have, for propensity score estimation.